Hello and welcome back everybody to this second video on the graphing of functions. Second and last, I would say. So functions, graphing, part 2. So what are we going to take a look at here? Well, last video we saw lines, parabolas, and absolute values. So today we have 3 more on the agenda. The fourth one is called the rational function. Okay, rational function. Well, the rational function is very important in calculus in many ways. In its simplest form, so in its simplest form, it actually looks like the following. In its simplest form, we have y equals the rational function. Rational means ratio, ratio means fraction. Y equals something like 1 over x. So this is the most basic rational function. There are other versions. We'll take a look at some of them, but that's the most basic one. This is a very interesting function because of its applications to calculus. So what can we do with this? Well, we can try to actually sketch its graph, really. And to sketch its graph, we can actually take table of values. Yes, that's the usual standard way to do that. Now, basically, I'm just going to try a couple of values here. So -3, -2, -1, 0, 1, 2, 3. And these x's I'm going to put into my function 1 over x. So that's very easy, -1/3, -1/2, -1. Something interesting happens at 0, because 1 over 0, as you may recall, does not exist. There is no value for 1 over 0. 1 over 1, 1 over 2, 1 over 3, and so on and so forth. Should you plot this on a Cartesian set of axes, you would actually get something quite famous, to be honest here. So x and y. So plotting all these points, I'm just going to make a rough sketch of what you would get here. The more points you have, the more precise your graph, but I'm going to be just happy to have a shape that looks like this. Now that is remarkable for a couple of reasons. See here, the part of this graph that's actually get closer and closer and closer to the y-axis, and it's the same thing here, getting closer and closer and closer to the x-axis, and it's the same thing here, and it's the same thing there. These are called asymptotes. So this graph has 2 asymptotes. What is an asymptote? What is an asymptote? It's a line towards which the graph gets closer and closer without ever touching it. Without ever touching the line, touching the asymptote. So in this case, the y-axis, so here, x equals to 0, is a what we call vertical asymptote. And this line here, the horizontal line, the x-axis, which is the line y is equal to 0, is a horizontal asymptote. Horizontal asymptote. So these are the main characteristic of that basic function, the rational function, with a graph that looks like this. Basically, I sketched this free-handedly, but you can probably tell, for example, that here you have the point 1, 1 on the graph, like we have here 1, 1. And here you have the point -1, comma, -1, right here, right? So you can see that those points will actually fit this curve quite well. Now, like I said, this is the limited version of the rational function. 1 over x can actually be made to be more interesting. We can beef it up a little bit. And here's how we're going to do that. So let's get rid of all this. All right, so what's this rational function look like in general? So in general, the rational function looks like what? Well, that's a pretty bad like. Looks like, well, you might recall y equals a over x minus h plus k, right? So this is the usual high school way of expressing this with an h and a k. The h and the k have obviously great significance for this graph. So let us see where it is. So where x equals h is a, what is x equals h? Can you fill in that blank? What is x equals h? What makes the denominator 0? In the previous function 1 over x, x equals to 0 made the denominator 0, and it ended up being a vertical asymptote. So that's exactly what this is. X equals h is a vertical asymptote. So I will underline this because it is important. Vertical asymptote. And we have the other guy here standing out, the k. So y equals k. This one is a, well, you can probably fill in that blank, right? It's a horizontal asymptote. So these are the two important features of this guy. Also note, I'm going to put that over here if I want to have some room. Also remark, if a is greater than 0, a being the numerator of this function, then the graph is going to look like the good old 1 over x that we had before, with the two halves in this way, first and third quadrant. But if a is actually less than 0, then what we have is actually, well, the opposite. We have this and that, right? So this time the curve actually moves in the second and fourth, 2 and 4 quadrant, right? So it can do a better graph than this. If a is greater than 0, you're going to get something that looks like this. And if a is less than 0, you're going to have something that looks like that. Okay? So this is little pointers that we don't really need to know that for sure. but if we do, it helps to sketch the graph a little better. So let's take a look at an example here. So I believe in this section, I have it here. This is example 4. Let me just grab this here. Example 4. Sketch the graph of y equals, what do we have? 3 over x minus 1 plus 2. All right, so that's not very, very hard, is it? I mean, we got all the information we need here to actually get the sketch that we want. X minus 1, we shall compare this to x minus h. X minus 1, we shall compare this to x minus h, out of which, what will we get as a value for actually h, not x, my bad, for h? Well, bring it over, the x's cancel, and you will get that h is 1. As for the k, well, compare this. The k is the trailing value at the end of the fraction, and that trailing value here is 2. So what did we find here? We found the vertical asymptote, and here we found the horizontal asymptotes. So these are my 2 asymptotes. Good. So I will sketch the graph of this according to the asymptotes we found, and also the value of a. What is the value of a? A is what's on top of the fraction. A is what's on top of the fraction. A is 3. It's a positive value. So we will remain in the first and third quadrant. Let us put in our asymptotes. Vertical at 1. Horizontal at 2. And then, perhaps a little higher here. And then, since we have our asymptotes, and we know that a is positive, it's going to be looking like this. Notice that I lean closer and closer and closer to this line y equals 2 without ever touching it, because it's an asymptote. And it's the same thing here for the line x is equal to 1. And then I do this. Like that. And if you want a little more precision on this graph, if you want actually to get a couple more points, you can actually try to find, say, the x-intercept or the y-intercept. That'll give you a little more precision of where this graph actually shows. This is the easiest one to find because the y-intercept we have when x is 0. So if x is 0 in here, 0 minus 1 is minus 1. 3 divided by minus 1 is minus 3. Minus 3 plus 2 is minus 1. Yes. And we could also find the x-intercept, but I want to move on to the next thing, so I'll leave this to you as an exercise. What is the x-intercept here? Go in there and replace y by what? 0, of course, and you will find it. So this is roughly how you would sketch the graph of a rational function. Once you have the vertical and the horizontal asymptote, this is really not hard to do at all. All right, so for those who are keeping track, that was a 2.5 star example. I could write it down if you want. That was 2.5 stars if you are keeping track of this sort of thing. All right. So that's enough for this type of function. Now let's take a look at the second last of the bunch, the radical function. So radical function, radical, something with a radical means something with a root. That means something with a root. The most common being obviously the square root. So in general, what does it look like? In general, we have y is equal to a, and I'm going to use a square root here. You can have cube roots, fourth roots, all sorts of roots. And I'm going to have x minus h plus k, the famous hk notation that we are used to from high school. Hk is a vertex. Hk is the, I'm gonna put that between quotation marks because it's not vertex in the sense of a vertex for a parabola. It's another type of vertex. So is a vertex, because vertex really means like a summit point, like a key point, a top point. That's not really a top point, but it's a very important point on the curve. So it's called the vertex of the function. Also, if a is positive, if a is greater than 0, then we are going to expect the type of shape that we know as square roots to have. The shape is going to look like this. This is the typical shape of a square root where a is positive. And here's your hk. And here's your hk. Now, if a is negative, then we basically have something that actually looks like what? Something that actually looks like this, right? Something that actually looks like that. No, that's not true. I lied. Something that actually looks like this, where this is your hk. Okay, so that's a bracket, hk. So the shape of the root will actually go downwards if the a is actually negative. All right, do have an example for this, I believe. This would be example 6, I think. Would it be example 6? Not sure. Maybe example 5 according to this sheet, but who cares? This is, again, not extremely difficult, so 2.5 stars. Sketch the graph of y equals, what do I have here for you guys? 2 root x plus 1, and trailing outside is a -4. Looking good. Let's put that over here. All right, our job, find the hk. Find the hk. So find where that root actually begins. So, what do we have here? What do we have here? X plus 1 is to be compared with x minus h. So x plus 1 is to be compared with x minus h. X plus 1, x minus h. If you eliminate the x's from here, you'll have 1 equals minus h. That means h is -1. As for the k, it's the trailing value at the end, so k is just -4. The a value, what's in front of the root, is positive, so we're going to open up to the right at that point -1, 4. So -1, 4, probably should have something more on the left than on the right here. So here's x, here's y. My point -1, 4, I'm going to put it over here. So -4, -1, and like that. Good, and then basically I just sketch the graph of this. So it's going to go like this. Start here. A is positive, so it's going to open up like that, and you go like this. And this is your hk. And as you can see, once again, here it is possible to find the y-intercept of this very easily by, in the function, replacing x by what? By 0, of course. So if you replace x by 0, let's do it quickly. 0 plus 1 is 1, root of 1 is 1, times 2 is 2, and 2 minus 4 is minus 2. And if you wanted to find the x-intercept, you could by doing what? You would replace y by 0. Good. I will leave this to you as an exercise, what happens when we leave y is equal to 0, and you can find that point for even more precision on the graph. Good. Excellent, excellent. So like you can see here, this is not super complicated, right? One little remark before we go on about this radical function. So let me put it over here. So one little remark. This actually, just like the rational function, doesn't have a domain of R. It actually has a restricted domain. The domain, remember we spoke of this in an earlier video? The domain of such a function is restricted. The domain of such a function is restricted to, okay, what's the general thing? I'm going to write it down again. Here, this is like a root of x minus h plus k. Remember, the domain is the set of x's that you can actually put inside the function. Well, we have a root here. That means we have to be careful because we can't have the roots of negative numbers. So the inside of the root, which in this case is x minus h, is not allowed to be negative. How do I write this in math? I say x minus h cannot be negative. That means it has to be positive. Yes? So x minus h has to be greater than or equal to 0. That is, i.e., that is x greater than or equal to h. So that's the type of notion I guess we have to be aware of when we sketch a square root. It has a restricted domain due to the fact that the inside of the root can never be negative. All right. Let us see if we can cover the last type of graph that we are going to encounter in Cal 1. All right. Okay, so 6. These are called piecewise functions. Okay, what is a piecewise function? It's probably something you've seen in high school. Piecewise means that the function is defined by pieces. So what you're going to have is something like y equals 2, and then y is not one single thing like a rational function or a radical function. It could be several things. So that's why we put a curly bracket. And then we're going to say, no, that's a bad f. We're going to say that y can be f of x for certain values of x. X is greater than or equal to a, say. And then it can be a completely different function, so g of x, if x is less than a. Right? So this is a piecewise function because it's defined in terms of pieces. I've defined a function here that has 2 pieces, f and g. But clearly you can have functions with 3 pieces or 4 pieces or whatever. These are functions that are useful to be able to graph when we hit the part of calculus called continuity. So let's do an example of what this may be. I have it here. I have here as example 6. And perhaps because we have different types of functions here, I'm going to make this 3 stars. And the question is the same in the video and this last video. It's always the same. Sketch the graph. Sketch the graph of y equals, all right, what is my y here? Y is x squared minus 2x minus 8 if x is less than 1. So you see here, there's a segment of this part that is a parabola. And then there's another segment that is just a point. The function is actually equal to just plain 0 when x is 1. This here, this second part of the piecewise, is just a point. It's the point 1, comma, 0. And then there's a third part to that. It's a line, x minus 3, and that actually is what the function looks like when x is greater than 1. So we want to sketch the graph of this piecewise function, which has 3 pieces. So the strategy is pretty simple. What's going to be our strategy to do that? Well, it's a piecewise, so we're going to sketch in pieces. So basically, step 1, sketch the first curve, sketch the first curve only for x less than 1. Then sketch the second curve, sketch the second curve only for x equals 1. And 3, well, sketch the last part, so dot, 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 when x is greater than 1. So we have 3 graphs to do, and then we're going to have to keep some parts and erase some parts. Let's see what is meant by that. The first one, x squared, there's a y here, x squared is the first term, minus 2x minus 8. This is a parabola. We've seen how to sketch that in the previous video. Do you remember how to sketch the graph of a parabola? Well, if you don't, you can look at your notes. You can relook at the previous video. I'm going to go relatively quickly over this. Sketching this requires finding the zeros. So this is done using the quadratic formula or factoring. I'm going to factor this into x minus 4 and x plus 2. And that is the correct factoring for this. And my zeros are found by letting each of these brackets equal to 0. So x minus 4 and x plus 2 are both equal to 0. So here are my 2 x-intercepts, 4 and 2. As for the vertex, if you paid attention to the previous video, you've learned, relearned, remembered that the vertex is the midpoint between the 2 zeros. So I'm going to add my zeros and divide by 2 to find the average point. That's 2 over 2. That's 1. All right. So basically, what I'm saying is that here's my standard Cartesian plane. And what I have over here, I'm running out of space. What I have over here is what? 4 as an x-intercept, minus 2 as an x-intercept, and 1 as a vertex here. Basically, this has an a that is positive. In front of x squared is a positive 1. So that's basically, I don't know where exactly this is. I can calculate it, I guess. I'm a bit lazy. So if x is equal to 1, you put it in there, you're going to get minus 9. Right? 1 minus 2 minus 8, that's 1 minus 10, that's minus 9. So your graph, this is your vertex at 1 minus 9. So it looks like this. Apologize for the lack of symmetry. So ballpark. Now, this is the entire graph of the parabola. Now, here's the thing. We ought to keep this only when x is less than 1. Ha! So that means we're not allowed to have anything larger than 1 or even equal to 1. So where's the part that is less than 1? It's on this side, right? Because on the other side is greater than 1. So I'm going to keep what's on the left side of 1. I'm going to keep what's on the left side of 1 and erase the rest. And that's the graph of the first part. And that is the graph of the first part. All right, I'm just also going to get rid of this ugly arrow. And that's the part. Now one detail remains to be checked out. And what is that detail? That detail is at the point 1, right there. Right? This is where the graph actually ends. Is this an open point or is this a closed point? So do I fill the point or do I keep it open? Answer, x strictly less than 1 means an open point. Only when x is less than or equal to 1, then we should actually fill the point right there. So you see, this is the first third, if you want, of the graph. So it starts like this. Then we go on to this here. If y is 0, x is 1. So the second part, if y is 0, x is 1. Well, that's the point 1, 0, isn't it? That's the point 1, 0, which is right here. That's the point 1, 0, right on the x-axis. So that was pretty easy. And 3, the third one, is x minus 3. Oh, that's a line. Y is equal to x minus 3. That's a line. I know very well how to sketch the graph of a line. I take a couple of points. Technically, I should be taking the x and the y intercept. And if I do so, if x is 0, y is minus 3. And if y is 0, x is 3. So this line actually goes through 0, minus 3 and 3, 0. 0, minus 3 and 3, 0. It's going to go like that. It's going to go like that. Let's say this is the point 3. So 1, 2, 3. And 0, minus 3 will actually be kind of here. So maybe something like this. I don't know. Something like that. Ballpark, not to scale. And then I have to apply the so-called restriction. Oh, this is good only when x is greater than 1. All right, so here's my 1 threshold value. You want to keep only what is to the right side, greater to the right side of 1. And that means you erase what's on the left. So what's on the left is gone. What's on the left is gone. All that is gone. My magic finger erases all this. And then the question arises, what is this point? Is it a closed point or is it an open point? Well, I look at my piecewise and it says strictly greater than 1, not equal to, so that is an open point. It will actually be of interest later on to know the y value that corresponds to this open point. For that, super easy, nothing is easier. I will replace x equals 1 inside my function here. So 1 minus 3 is minus 2. And that would actually be the y component, if you want, the y height of this open point. And that is actually the graph of this function. That is actually the graph of this function. So you have here a nice little example of a piecewise function. Good? All right, that's it. That was my last example for today. So we'll do some more of these exercises in class. Sorry if this video took a little longer than the other ones, but now we're done with graph sketching. We can move on to the operations on functions in the next video. All right, so that's it for today. I'll see you soon. You take care of yourself.